I talked about this at the end of class yesterday, but I'm just going to touch on it again since I actually printed out the PowerPoint for you. Or at least the 3 slides I had to add to it. Okay, so weighted mean is that top slide. That's where you have different weights. So they could be percentages. They could be, like, honestly, like how much interest your bank pays you for a savings account. They use a weighted mean to get your average amount that you've had in the bank that month. And then they'll pay you interest based on that. So you take the weight times whatever your value was for that category. That's how much it contributes to the mean. And then you add them all up. And I'll put the formula that will be on your formula chart, dual credit, for weighted mean. The W stands for the weight. The X is your actual score in this example. So since I talked about it yesterday, I won't talk about it too much unless y'all have questions on it. Any questions on this example? Okay, one I didn't talk about, but I needed to talk about was now it doesn't want to go. Is this dead? No, not dead. Okay, the mean of a frequency distribution. So we're on that one-page handout I gave y'all.
Oh, okay.
I just went on and put an example on there that we all wouldn't have to worry about writing it down and all that.
Yes, sir.
So for the mean of a frequency distribution, AP, you can write this on it. Dual credit, I for sure want y'all to write this. This is what you call grouped data. This is grouped data. Because we're not doing individual data points, we're grouping them into classes, like a frequency distribution. And the reason I make the grouped data distinction is on your formula chart, it'll say, this is how you find mean. And then the next formula might say, this is how you find mean for group data. So then you can, oh, group data is frequency distributions. So anyways, the main thing here that's different, or really I guess the whole thing is almost kind of different, but what you do is you find the midpoint of your classes. So the first 2 columns are just our basic frequency distribution. Then we have to find the midpoint of our classes. So that's where you add them up, add up the limits and divide by 2. So the midpoint of the first class is 31. Midpoint of the second class is 36, and so on. And then you have to multiply the midpoint times the frequency. What we're doing is we're saying, okay, well, in this first group of cars, on average, they get 31 miles a gallon because it's a 4 mile per gallon range. So we're just going to say everyone in that class gets on average 31 miles to the gallon. Well, for those 11 cars, you multiply the frequency times that to get you the summation part of it. So that's x times f. We do that for all of our classes and add them up. So in our case, we got 1,085. Well, as with any average, once you add them all up, you have to divide by how many you have. We have 30. So 1,085 divided by 30, that would get you approximately 36.2 miles per gallon for the whole average. I know I kind of ran through that one quick, but does that make sense at least?
The 36.2, so that's the mean of the distribution chart?
Yeah.
Okay, I was just confirming.
That's our mean of our frequency distribution, 36.2. Okay, at the end of class today, we're actually going to build on this example and take it one step further based on what we learned today. So, speaking of which, let's start 4.2. So yesterday we talked about the central tendency of the data, meaning we looked at mean, median, touched a little bit on mode, not much. Now, central tendency is great, but why would I even want to know about variability? I mean, it's because there's variability in virtually everything. We mentioned, I think it was the first lecture, if we had a 12-ounce can of soda, would you expect there to be exactly 12 ounces on the dot?
Nope.
No. There's going to be variability in there. Now, what would you hope? Would you hope there's a lot of variability or a little? A little. If you open a can of, I guess since we're in Texas, Dr. Pepper, and you look in there and it's only 2/3 full, you're going to feel like they just robbed you. You paid $1 for this, and it's only got 8 ounces in it. But yet it's a 12-ounce can. So you don't want that much variability. This allows us, the study of variability allows us to distinguish between usual and unusual values. So that 8 ounces, that really should have been thrown out at the factory because that machine's messed up on that one. And reporting only a measure of the center does not provide us with a complete picture of the distribution. Sure, those cans on average have 12 ounces, but if the machine's working right, it better be really close to 12, not trying to overfill the can, and not giving you just half a can. So, let's look at these 3 dot plots. If you look at them, you'll notice that the mean and medians are both at 45. But they have different amounts of variability. The first one's all spread out evenly. Second one, we got the 20 and the 70, but then the rest of them close together. And then the last one, everything is packed in there tight.
Mr. Schultz,
Yes.
on that middle chart with the 20 and 70, would that be considered outliers or no?
Yeah.
Okay.
Those would be outliers. Those would definitely be outliers. So how do we describe variability? And did everyone get the blanks on the bottom of page 6? No? Okay. Okay. How would we describe this variability? Well, the simplest and the easiest one to compute is the range. So if we look at, bless you. If we find the range, that's just the difference between the largest and the smallest values. I think we've already kind of touched on range a little bit already. The range is the maximum minus the minimum. So let's calculate the range for those dot plots. In the first dot plot, what would our range be? 70 minus 20, which is 50. What about the second one? 70 minus 20, which is 50. And then the last one? 10. 50 minus 40 gives us 10. So the first two data sets have a range of 50, but the third has a much smaller range of 10. I don't know why that said outlier. That's why I paused and looked. Much smaller outlier? Much smaller range of 10. So range is okay, but how many, let's think of it this way, how many data points does range use? How many points do we need to find the range? We just need 2. Do 2 points give you a good representation of the data? No. I mean, think about it. These top 2 have the same range. So if I just told you, oh, the range is 50, okay, great, but are the points spread out? Or are those 2 outliers, like Raleigh mentioned, and then everything else is just clustered inside? So it's easy to calculate, but we only use 2 points. So let's talk about something that's a little bit more useful, hopefully. So if we talk about deviations from the mean, well, those are the differences that each observation is away from said mean. Let's say our average was X bar. Then the deviation from that mean would be like X1 minus X bar. So the first observation, X sub 1, minus the average. That's how far away from the average it would be. And we could find that for every observation. But if we think back to yesterday, what did I say the mean did to the distribution? I'll give you a hint. That's why I was using the ruler. The mean balances the distribution. So one drawback to just using deviations is that if we add them all up, they're going to equal 0. Because the mean is our balance point. Unless you round it or something, they equal 0. So the average deviation from the mean would always be 0, and we can't use it as a measure of variability. So we've hit yet another roadblock. We thought we were getting somewhere, and roadblock. we will use this a little bit in the future, so let's get some practice with it. Let's go back to our Lake Sam Rayburn example that we started yesterday. So suppose we went fishing and we caught 6 fish from the lake with the lengths of 3, 4, 5, 6, 8, and 10. We want to calculate the deviations from the sample, or deviations from the sample mean, yeah. What do we have to find first to get the deviations? The mean. We've got to get the mean first. So find the mean right quick of those 6 points. And let me know what you get when you calculate it. Once we get the mean, let me know what you get. It's 6. Yep. So now let's use our mean to find the deviation from the mean of each of our fish. So to do that, we would have to say, okay, we just have to go through the chart. Well, our mean is 6, so 3 minus 6. What would that get us? Negative 3. Then we go to the next one, 4 minus 6. Yep. And then just fill your chart out. Okay, so if we fill our chart out and then we add them all up, what should we get? 0. So it's definitely 0. Will this sum always equal 0? Yes, it will. Most definitely. I mentioned this earlier, but again, the mean is considered the balance point of the distribution because it balances the positive and negative deviations. So will it always be 0? Yes. And that's one way when you're calculating standard deviation of just normal data, not group, not a special case, just calculating it for normal data. That's one way you can check that you're on the right track. If you make this column and then you add them up and they're 0, you did at least that part correct. But let's hang on. Before I say what I was about to say, let's just talk about this for a second. A particular deviation would be positive if the x value exceeds the average, and negative if the x value is below the average. So in general, the greater the amount of variability in the sample, the larger the magnitude of the deviations. So notice it says we're ignoring the signs. So if there's a large amount of variability, then our deviations would probably be larger. So another measure of variability of the data set uses the deviations from the mean. So they use what we just calculated. So going back to our example, what was the sum of our deviations on that example we just did? First, let me back up. Did y'all catch that magnitudes blank? Or did you catch it? Okay. So what was the sum of our deviations in our chart that we did? 0. So using that, can we find an average deviation? What's 0 divided by anything? So does that tell us much? No. So what can we do then to the deviations that would allow us to find an average? If I can't just find the normal average, what can I do to where I can use that information? So let's go back to our chart and take a look at it. What can I do to these numbers to make it to where I won't have any negatives? Think back to like algebra 2. What's something that's always positive? Well, if I go through and I'll square them all, what's negative 3 squared? 9. Negative 2 squared? Negative 1 squared? Ah, there went my negatives. So one thing we could do is square the variances and then find the average of those. That average, or that estimated average, I should say, is called the variance. So if we square them and then find the average of those, that's called the variance. So here, okay, I get it. You add them all up once you square it. But it says to divide by n minus 1. On a normal average, we divide by just n. So let's talk about why that is. It's called a degree of freedom. So on a normal average, they can be anything they want to be because we'll just add them up and divide by how many there are. But think back to our fish example. We said the deviations must all add to 0. So can that, if we had the same first 5 observations, could that 6th one be anything it wanted to be and have that still equal to 0? You'll see.
I'm confused with your question.
Okay, I'm gonna go back to the chart here in a second, and then I'll ask it again.
All right.
I'm just letting y'all get this written down. Okay, let's go back to the chart right quick. So, what I was asking was we have these fish right here, right? Let's say the first 5 are the same. We just happened to catch them, and that's how they worked out. Could this 6th one be anything other than 10, and this still be equal to 0 down here? Could this be like 11 or 12? And keep the same average and everything? No. So if we want to keep everything the same, this one has to stay 10, which means that one has no freedom. It must be 10. So that's what we mean by, over here, degrees of freedom down here. 1 does not have any freedom, so we gotta take that degree away from our equation. Because it can't be anything other than what it is. Now, so back to page 8. The population variance is denoted by sigma squared. This time we have a lowercase sigma, which is just an O with a tail. So lowercase sigma with the square, that's the population variance. Yesterday, if you remember, we said the population mean was that mu character. This is sigma squared. So suppose that everyone in the class went out and we had a day, they told us we could all go fishing. And we all caught 6 fish. Would each of our samples contain the same 6 fish? Most likely not, no. Would our mean lengths all be the same? Probably not. We all caught 6 different fish. They're probably all different lengths. So, yeah, we're probably not all going to be the same. Which means our samples would also all have different ranges. So the customary way to prevent negative and positive deviations from counteracting one another is to square them before we add everything up. And then a simpler explanation for degrees of freedom, the n-1 part, and the denominator, is that it tends to produce better estimates than just using n. And this is kind of a little deeper. You don't have to know this, but just a little tidbit of information. The main reason we do it is when they developed all the statistical theory and whatnot, they used calculus. And when we converted all that from calculus to just algebraic equations, that's how we got the n-1. Trust me, I won't have y'all know any calculus.
Mr. Schultz,
Yes.
were you in a frat house in college?
Was I what?
Were you a frat guy in college?
Nope.
Not alright.
I was still the bookworm.
Nothing wrong with that.
Nope.
What's a frat?
Fraternity, it's
Like a club in college.
Yeah, it's like a club, a Greek club usually. You have good ones and bad ones. I mean, some all they care about is partying and everything, and then there's others that are better.
Like school moves?
Like what?
School moves?
Yeah. Okay, so degrees of freedom will be revisited again in chapter 8. So don't worry too much about the degrees of freedom right now, other than the fact that when we do variance and standard deviation, we have to use n-1. You don't have to know right now that it's called degrees of freedom. We'll talk about that in chapter 8. Which sounds like a long ways away, being that we're on chapter 4, but we're going to skip chapter 5 and go straight to 6. So 8 will be here before we know it.
Is our next test Thursday or Wednesday?
Thursday.
Thursday, dang, we got another test before we do.
No, they test the same day y'all do.
Oh, I thought it said Wednesday and Thursday.
That's for geometry.
Oh, I got you.
No, everyone in here will be testing on Thursday. And then after that, dual credit, y'all's tests will become a little bit more frequent. In the sense that they won't take like 3 tests before you take one. They'll
Don't we only have like 3 after that one?
3 and then the final. Yeah.
Alright, no, I'm all good.
Okay. So let's go back and think back to our fish example. So we calculated the deviations here. That's what we did in that first example. I want y'all to go through and square these right quick. Or I'll say y'all. Let's just do it together because it's just squaring integers. So what's negative 3 squared? 9. So negative 2 squared?
4.
Negative 1 squared?
1.
And so on. So we just went through and squared that middle column. Now add them all up. Yep. We're calculating the variance. That's what we're in the process of doing.
$34.
34, that's right. So to get our variance, we need to divide this by n-1. What's our n?
34.
Our n is 6.
Oh.
n-1, so 6 minus 1 is
5.
5. So that's, we divide 34 by 5. And what's that get us for variance? 6.8, that's right. Now I realize here that didn't show much work. I really would like y'all to at least write the formula and then just say, okay, that's equal to 34 divided by 5. If you have the table and then you write the formula and then just plug in 34 and 5, I'll understand what you did. Now, our units for variance are squared. So if you wanted to make note of that, our variance technically is 6.8 inches squared. Now, does that make much sense? Square inches on a fish.
Yes.
For the length? Does that make sense?
I'm just saying it is because I've gotten it right twice now. So.
No, it doesn't make much sense. Inches squared for length of a fish. It's like, what, inches squared is area, not length. So that's where the standard deviation comes in. The sample standard deviation, which we just denote by S, is the positive square root of the sample variance. So the formula for standard deviation looks nasty until you realize that really this is just S squared underneath the square root. So the way you usually would find it is find S squared, find the variance, and then just square root it. And you get the standard deviation.
Mr. Schultz,
Yes.
I was gonna say, did you hear about Longview? The football?
Mm-hmm.
They got into like a big old brawl during the scrimmage with Texas High, the people that beat us last year.
Uh-huh.
And like everybody stayed in the stands to watch Lobos, because they ended the scrimmage and they made the Lobos run 100-yard sprints for 30 minutes straight after the scrimmage.
Wow. Okay, so the population standard deviation is denoted by just sigma. We said the variance was sigma squared, so it only makes sense that the standard deviation is sigma, the square root of sigma squared. Hang on, we got a question. Let's see. Why would it not work to use the same value? Okay, so real quick, and I don't know the exact answer to this, other than tying it back to the calculus that I mentioned earlier. Olivia asked in chat, back when we talked about here, we need to square it. She asked, why couldn't you just use absolute value? Because that gets rid of your negatives. And like I said, I don't know the exact answer other than the fact that it has to do with the calculus-based equations. They used integrals and derivatives to calculate standard deviation and variance. So hopefully that answered your question, Olivia. Okay. So a large amount of variability in the sample is indicated by a relatively large value of S squared, or your standard deviation. So if you have a lot of variability, then you're going to have a large variance. If you don't have much variability, or it's close to zero, you'll have a small variance. But as we mentioned, for statistical purposes, standard deviation is usually the desired quantity. Think back to our fish example. The variance being in inches squared doesn't make much sense. So if you take the square root of it, then it just becomes inches. You're like, okay, I know inches squared. I know inches. I don't know inches squared for length. So it makes more sense. That means that's why most commonly we use mean and standard deviation for center and variability. Or another way to say it, central tendency and spread. Mean is your measure of central tendency. Standard deviation is usually your measure of spread. So let's calculate the standard deviation for that fish example. Remember, all we have to do is take the square root of our variance. The variance was 6.8. So you take the square root of it, and that gets you approximately 2.608 inches. And as we'll learn, I believe it's on, it may be Tuesday actually. I was going to say Monday, but I think it's actually Tuesday. Most of your data will be within 1 to 2 standard deviations from the mean. Most, if not all, of your data. So for our fish example, our sample deviates from the mean of 6 inches by an average of 2.608 inches. Okay, so I'm going to give y'all let's say 5 minutes. I want y'all to try to get as far as you can through this apple weight example. I'm going to set a timer for 5 minutes. Remember, we first need to calculate our average. So first we need to get X bar. This middle column, that's your deviation. So you subtract 7, in this case our first observation is 7.52. Subtract that from your average, whatever you find your average to be. And then this last column, you just square the middle column. So I want you to calculate the standard deviation of the sample. See how far you can get in 5 minutes. Let's see if y'all can beat third period on how many you get finished in 5 minutes.
Finished?
Yeah, see if you can get finished. Third period had 2 get finished. Can y'all do the same? And you can work with your neighbor if you need to. Maybe divide and conquer.
Oh, dang, I gotta restart.
Five minutes.
We got 2 minutes. I have no clue how people finish this.
How close are y'all? Anyone getting close?
Nope, not really.
No.
We're good another 5 minutes.
What's that?
Can I get another 5 minutes?
Yeah, I'll give y'all a little bit more time, and then we'll go over it together. Oh. Okay, so I kind of stretched the truth. Only one finished in 5 minutes last period.
Could you possibly elaborate on who that might have been?
They were in AP. What were you saying, Will? No, he's actually virtual here with y'all. Those of y'all that are virtual, does anyone have an answer possibly?
I don't have to come on there, you got it.
Okay, they're saying not yet.
Is there like a 5-digit decimal on this, or am I like off?
For which column? Are you talking about like that third column of calculations?
Yeah.
If you use the full decimal, yes, it's actually 6. I did 6 digits on
Okay.
most of them.
I was just making sure.
If you use the whole one, yeah.
Am I supposed to use the whole one?
I would at least use 4 digits.
At least 4?
At least 4, yeah. I use the whole one just because in grad school, not grad school, but undergraduate, upper level, undergraduate classes, meaning bachelor's classes. They like told us, do not round until the end. I'm like, okay, yes sir, I won't round until the end. So I just got in the habit of it.
Mr. Schultz, I think Mac canceled her game.
Uh-oh.
I think they're scared.
Y'all beat them last year, didn't y'all?
Yes, sir.
So I get to hold on to that win another year.
Yeah, but I wanted to play them. I need film.
Oh. Olivia got it, and she got the right answer. Has anyone gotten to the sum of the last column yet?
I'm about to be there.
About to be there? Don't look, don't look, don't look. You're not seeing anything. You don't see anything. I'll just leave it up there. What the heck? I'll just leave it up there. Y'all need the numbers anyway, so. If you haven't gotten it, I'm helping you out, giving you some numbers.
I got this.
I'm not giving you all the numbers, but giving you some of them. Can you come in Monday morning? If my door's open, you can. Yeah. Assuming I don't sleep late like I did this morning.
What is considered sleeping to you?
6:15. I usually wake up at 5:30. I'm like, I don't need to set my alarm. I'll wake up. And I wake up and at 6:15, I'm like, oh crap. I can't do any work now before I leave the house. So I usually get up and like grade papers or something, and okay, I need to make my way to school. But didn't get to do that this morning. I still left by 7 and was up here by 7:15.
Calculate standard deviation after you get this number. Okay, good.
What are we down to?
4 digits, right?
Yeah. Okay, so I'm going to talk about the table real quick. So the average that you should have found is 7.424. That should have been your average. So in the middle column, you would subtract take all your observations and subtract 7.424 from them. And then in the last column, you square everything in the middle column. And when you add up that last column, you should get 5.3984. So if we write our formula down for variance, the summation was 5.53984 divided by, how many observations did I have? 10. 10 minus 1 is 9. So we have that nice long number. And of course, that doesn't divide evenly. And just to show how I like to use all decimal places it gives me, I wrote down that the calculator should have given you something like 615537778. It probably repeated sevens after that point. So that's our variance. But did it ask for variance? No, it asked for standard deviation. Standard deviation is the square root of the variance. So if we take the square root of s squared, you would get actually I did 5 decimal places, 0.78456. Final answer. That's our standard deviation. You what? Okay, let's go back to our PowerPoint. There's the right one. So, okay, so that's what we just found. They didn't fill the chart out. That's what you should find. I see some writing it down, so I'll hold up for a second. Okay, now, if that wasn't enough to make your brain hurt, wasn't that bad?
I feel like I'm having a good
Yeah, actually, that was the hardest problem today, so we're good. That was the most tedious of what I'm going to have y'all do, at least. I could have y'all do another tedious problem, but I'll go easy on y'all after doing this example. Okay, let's talk about a little different topic. This one deals more with medians. So the interquartile range, which we abbreviate IQR, is the range of the middle half of the data. So what advantage does the IQR, the interquartile range, have over standard deviation? It's resistant to outliers. Outliers do not impact IQR. Just like how yesterday we said the median is that if it's something is skewed, it gives a better example. IQR does a similar deal. It's a better description. And it's easier to calculate than standard deviation. The IQR is based on quantities that we call quartiles because we're dividing the data into quarters. So the lower quartile separates the bottom 25% of the data from the upper 75%. The upper quartile separates the top 25% from the bottom 75%. So that's what this chart is saying here. Go back. That's what this chart's saying. So here's our data. It's a symmetric normal curve. The first quartile is right here. It separates the top 75% from the bottom. The median, it doesn't have it on this picture. If you want to add it though, it's also called the second quartile, or Q2. And then the third quartile separates the top quarter from the rest.
What other class did we learn this in like first? I remember this from somewhere.
I'm not sure, honestly.
Could it have been algebra?
Maybe. I'll say either that or whenever y'all talk about median, because really all this is just an extension of medians.
I didn't know.
What geometry?
No.
I can tell you that. What geometry?
Okay. I forgot.
Okay, so finding quartiles. Finding the quartiles for sample data, you do that by dividing the ordered observations into a lower half and an upper half. If you have an odd number of observations, the median of the whole data set is excluded from both halves. You don't say, oh, I'm going to put it with the second or the top half. No, you just leave it out. Leave it out. So the lower quartile, which is Q sub 1, is the median of the lower half of the data set. The upper quartile is the median of the upper half of the data set. And of course, the interquartile range is a resistant measure of variability given by the upper quartile minus the lower quartile. Or you can say Q3 minus Q1. Q sub 3 minus Q sub 1. And again, if n is odd, it is not included in either the upper or lower halves. We totally leave out the median. The median is left out. It's all alone. If n is even, then the median is not actually even part of the data set. We have to calculate it. So this smaller example, I'm gonna give y'all a little bit of time to actually work it. The bigger example, I don't want to say I'll give it to you. You have to think about it some, but I'm not gonna make you order all those numbers. Okay, so first small example. A sample of 15 students with part-time jobs were randomly selected and the number of hours worked last week was recorded. Find the interquartile range for this data set. Okay, well, what do we need to do first? Before we can find the median, what should I do first?
Put in order.
Put the data in order. So let's put our data in order. I'm going to give y'all about a minute to put them in order. Then if you get it done before I move on, find the median. Okay, I got them put in order yet? And I'm still working. Still working? Okay, check your order. See if you, I bet you can probably figure out if you put them in the right order, but just to double check. So which one of these did you get as your median? Which one's in the middle?
I got 10.
Which 10?
Yeah, last 10.
The last 10, that's right. So now we can divide it into upper and lower halves. So the lower half is everything to the left of our median. Upper half is everything to the right of the median. Okay, so if we find the lower quartile, I kind of just gave that to y'all, but what's the median of the lower half?
8.
8. What's the median of the upper half?
14.
14. So now to get the IQR, the interquartile range, we have to subtract the upper quartile, 14, from the lower quartile, 8. And that gives you 6. So your interquartile range is 6. Okay. Questions on that example before we go to the big one?
Got a big one? Oh.
So the Chronicle of Higher Education, in their 2009-2010 issue, published the accompanying data on the percentage of population with a bachelor's degree or higher. In 2007, for each of the 50 states and the District of Columbia, they asked us to find the interquartile range. So what's our first step that we have to do? Get it in order. Now, for sake of time and the fact that y'all were good sports and did that other big example, I'll give y'all the order. And also the fact I hope that by the time you're juniors and seniors, you know how to put numbers in order. Hopefully. Okay, I'm going to move on with it. So we need to find the median of our data set. Since there's 51 items, that means I can sit here and count and get to the 26th, and that would be my median. So let's see, they're in rows of 10, so 10, 20, 1, 2, 3, 4, 5, 6. So the second to last 26 is your median of the whole data set. So now let's get the lower quartile. For the lower quartile, we want to focus on just the lower half of the data set. Well, there's 25 here. So that means I need to count to the 13th one. There's 10, 11, 12, 13. So the 24, that first 24 is the lower quartile. And then I'll go down here and count 13 from the end. And I think it's that 30. Yep, it is. So this 30 is our upper quartile. So to get the interquartile range, I'll subtract the upper, I'm about to say it backwards. I'll subtract the lower from the upper. So 30 minus 24 is 6. So that's our interquartile range. Okay, so 2 quick notes, and then I want to talk about that last slide on that extra handout I gave y'all. So the resistant nature of the interquartile range follows because of the fact that 25% of the smallest observations and 25% of the largest observations can be made more extreme without the range being affected. And then a little note on rounding. If you want to make sure you're protected against bad rounding effects, use 4 digits of decimal accuracy. So go to 4 decimal places. And then one last example. It's mainly directed at dual credit for the group data. This is on the back of that slide, that little handout I gave y'all, that single slide. I'm using the same data set that we talked about earlier on miles per gallon. If you find variance, your x will be your midpoint. Your average is like you found earlier. So that part stays the same. Where it changes is you have one extra step. You have to multiply x minus x bar squared times your frequency. Then add that up to get your total that you divide by the n minus 1 degrees of freedom. So you just have one extra step at the end here to calculate it. So, okay, today was long. I'm sorry. At least you get 2 days off now. So if y'all are working on the homework this weekend and you have questions, feel free to email me or send me a remind message. And when I get a chance, I'll get back with you. Homework? Okay, let me pause the recording.
Mr. Schultz, may I go ahead and football?
Yes, you may.
Could I have the soccer?
Have a great weekend, Mr. Schultz.
Y'all too.